Hi guys, we're back to talk about volcanoes. So far we have talked about igneous rocks, which are the kinds of rocks that form from volcanoes or from melts that solidify underground. And of course, the ideas about magma and lava were touched on in our discussion of igneous rocks. And now we're going to get into the actual kind of eruptive process that fuels these volcanic eruptions. And it's kind of very much of a chicken and egg issue between volcanoes and igneous rocks, because like which one came first. They're constantly cycling between one another. So some of the concepts that we've talked about so far will be important here, and vice versa. Okay, so first of all, I just kind of want to talk about how lava moves. So lava flows are a word or words that describe moving masses of molten rock or lava. And it also describes the kind of solid formation of sheets of solid rock, igneous rock, that form after these lava flows freeze. So we're going to talk actually about the kind of moving flows themselves at this point. And viscosity is a term that we talked about last week. And hopefully you'll remember that the viscosity of a material has to do with how sticky it is and how resistant to flowing it is. So certain lavas are very sticky, they don't move very well, and certain magmas are very sticky, others are not so sticky, and they are much able to flow much more freely and much farther and much more quickly. And whether something is viscous, sticky, or low viscosity, not so sticky, has to do with, one, the number of volatiles that are dissolved in it. So the more volatiles, the more water and gases that are dissolved in it, the runnier it's going to be, the lower viscosity it's going to be. Temperature has an impact. The higher the temperature is, the more fluid it's going to be, or lower viscosity it's going to be. And then we also mentioned that the composition, the mineral composition, has an impact as well. And so in general, we said those minerals that are lower in silica, that are higher in metals, which we would call mafic materials, or basaltic in terms of lava flow. Lava and magma can be referred to as basaltic because basalt is the name for the rock that forms from an extrusive mafic lava. Those are going to be more flowy, lower viscosity. And then intermediate composition materials that can be called andesitic when we're referring to a flow are of intermediate viscosity. And then felsic composition materials, which can be referred to rhyolitic, which of course is the name for the rock that's formed from this ash that is formed when the lava is so sticky it doesn't really flow out of the volcano at all, but instead freezes up into these tiny little solid chunks of mineral and glass that then get compressed into an ash deposit. So again, the mafic is going to be lower viscosity, and then the felsic on the other hand, or the basaltic is going to be more mafic, and the rhyolitic or felsic materials are going to be higher viscosity or more viscous. So a lot of this has to do with the actual mineral structure, and we talked about this, or we looked at this diagram before when we just talked about what minerals look like and what kind of cleavage they might experience based on different zones of weakness within their structure. And we said at the time that minerals like quartz and feldspar have this very complex three-dimensional structure that gives them strength, but it also makes them clunky and sticky. Whereas minerals that are intermediate would be formed from these like sheets that are a little bit more slippery, and then minerals that are kind of mafic in composition, things like olivine or pyroxene, have much simpler structures, and so they are much less likely to get kind of tangled up, and they are able to therefore flow better when they find themselves in a melt. So basaltic flows, which are made up of these more mafic materials like olivine and pyroxene, are going to therefore be less tangly, less sticky, or lower viscosity. They also tend to have hotter temperatures, because remember, these minerals tend to form or melt at particularly high temperatures. So lower temperature melts would be preferentially made up of more felsic minerals. And they stay hot even after they come out of the volcano. The lava will freeze around the exterior of the area where the lava gets exposed to the surface to form these lava tubes. And then the lava can continue to flow inside the tube, being insulated or protected from losing heat to the colder air by this kind of frozen tube of lava outside of it. So that helps it keep hot and flowier longer. I don't know if flowier is a word, but allows it to flow longer. As a result of these things, these basaltic flows can move pretty quickly and pretty far compared to other kinds of lava flows. So near the summit, they might move up to like 30 kilometers an hour, or like somewhere in the low 20s, 22 miles an hour. And then after they move a little bit away from the vent, they're going to cool down, they're going to be more sticky, they're going to be more viscous, and they're going to be flowing slower, more slowly after that. And they might be able to move up to like 10 kilometers away from the volcanic vent. So that would be somewhere in like 7-mile range from a volcanic vent. So that's not a short distance. They can move a significant distance down the vent of the volcano, and we'll see this later. But volcanoes that are made up of a lot of basaltic flows make these huge volcanic structures, and so the lava flows a considerable distance down the side. And then really remarkably, there are these certain exceptions that we're going to talk about in a minute, usually associated with these hot spots, where sometimes we can have lava flows that are just truly extraordinary in their extent. So in some cases, we've noted lavas that have moved over 500 kilometers from where they came up to the surface. So that's like 350 miles, which is, of course, a very, very far distance. If you can imagine a volcano and then lava spewing that distance, that's pretty incredible. Okay, so here's what kind of some of these lava flows might look like. As we said, when the lava hits the cold surface or comes in contact with the cold surface, it loses energy to the air, and then it starts to freeze around the outside. But then in the interior, the insulation from the frozen lava tube keeps the interior lava hot longer. So these are kind of very small scale little lava tubes that lava is continuing to flow in. And then this is a picture from Lava Beds National Monument, which is kind of near here, a little bit north of here. And you can go around in all these lava tubes. They're kind of like a series of caves. And as you can see from the fact that this person is standing inside the cave, they're really quite tall. And these formed when lava was extruded from a volcanic vent, and then this ceiling froze, and then the lava continued to flow through it and eventually flowed all the way out of it, leaving this tube hollow. So it's, as I already said, like a cave that you can explore, which is pretty cool. I went there as a kid. I haven't been there recently, but it was a cool spot. Okay, so another thing which is a little bit sometimes difficult for people to wrap their mind around is, even though basaltic lava flows a lot better than other kinds of lava because it's lower viscosity, sometimes hotter, and made up of these more mafic minerals, except when you're really close to the volcanic vent, when it's first coming out, and we said it might be moving up to like 30 kilometers an hour, over 20 miles an hour. Once it gets a little bit away from the volcanic vent, it's not actually flowing that fast usually. So it's kind of this like slow speed natural disaster that's not possible to stop, but you're able to actually like take pictures and make observations and measurements and study this lava as it's flowing. And so this is a picture of some scientists in Hawaii standing in front of this volcanic flow. And again, it would not be safe to do this like right next to the volcanic vent where the lava was first coming out, and it was really hot and it was really fluid. But this is, several miles away from the vent. The lava is still moving, but it's kind of this slow motion disaster. And what we need to start to remember when we're going to think about these different eruption types is the fact that this is a rock. It's a molten rock, but the fact that this rock is flowing at all is pretty impressive. So even though this might not look as fluid as something like oil or water, we think of this in the context of this other rocky material as being very low viscosity. This is as low viscosity or as fluid or as runny as lava really gets. And so again, that doesn't mean it's rushing towards us like a tidal wave, but it's pretty fluid relative to the other kinds of melts that we would interact with. Okay, so as I mentioned a couple minutes ago, we have some instances that have occurred where we have tracked lava that has traveled enormous distances up to 500 kilometers away from the vent that it came from. And when this happens, it's usually associated with these phenomena that are called flood basalts. So just like floods are when we have lots of water, flood basalts are where we have lots and lots of basaltic lava that comes out of the earth all at once. And the theory is that this is associated with events that happen when new hotspots form and they kind of first break through the mantle and through the crust up to the surface, that there are these very extrusive, meaning like lots and lots of fluid is coming out of the earth, events that are associated with them, and we refer to these as flood basalts. So here's a map of different places on the earth where we have flood basalt activity that has occurred, and you can see some of this has occurred in like the Pacific Northwest, places in India and Siberia, South America, Africa, just about everywhere. And these, again, are associated with these either current or ancient hot spots. So zooming in on the United States, as you can probably notice, this is a picture of California, Oregon, Washington, and British Columbia. And so there's this area that's called the Columbia Plateau, and the Columbia River flows through the Columbia Plateau, and it bisects Washington State from Oregon State. And this whole Columbia Plateau is made up of these series of flood basalts, which is made up of many, many, many layers of basalt that represent these different kind of volcanic eruptions that occurred from the same vent or the same area of vents about 15 million years ago. So the Columbia River Plateau is an area of 220,000 square miles, so that's really big. And you can see from this picture on the left that there are all these strata, which is a word we use to refer to layers in geology, that kind of come up from the Columbia River. You can see the river in the very bottom right corner down here. And so all these different layers represent different volcanic events where we have this layer of basalt. And so on this map again on the right, you can see that this extensive area is covered with this lava flow. So it must have been able to travel quite a bit farther than just like 7-10 miles away from a volcanic vent when this area was being built, again, around 15 million years ago. So the green area is the Columbia Plateau, these 15 million year old basalt flows, and then this yellow area is showing the more modern Cascade Range volcanics. And then we also have, besides the Columbia River basalt group, Columbia Plateau, we also have a series of kind of basaltic, or we have a series of other eruptions that have been associated with a hot spot that is currently under the area of modern day Yellowstone, that has been responsible for some of the super volcanoes that have occurred in Yellowstone in the past that we'll talk more about later. And we think that that hot spot used to be located under northeastern California. And then the North American plate has been moving over time over the hot spot in a southwesterly direction. And so it's been moving and pulling the area in current day Yellowstone to the southwest, and now it's positioned over that hotspot that used to, about 15-16 million years ago, be located in Northern California. And so there's some thought that this Columbia River basalt outpouring of lava may be associated with that same hotspot. And so maybe the flows that we see and the volcanic eruptions that we see in northeastern California are associated with this same plume, same mantle plume that contributed to the lava in the Columbia Plateau, which is kind of interesting. So as we just mentioned, Yellowstone today is sitting over the same hotspot, and Yellowstone is not famous for lots and lots of basalt flows, because remember, these flood basalts are associated with when the hotspot first comes up to the surface, to the best of our understanding. So the hotspot that is now sitting under Yellowstone has been in existence for many millions of years at this point. It has, however, contributed to melting of crust and the formation of some large volcanic eruptions. So the Yellowstone area had some major eruptions just over 1 million years ago, and then 600,000 years ago. And that particular eruption was 1,000 times more powerful than the Mount St. Helens eruption, which is pretty impressive. And to remind you, the Mount St. Helens eruption was an eruption that occurred in southern Washington state in 1980. So today, Yellowstone National Park sits inside this giant caldera, which we'll talk more about in a minute, but it's basically this big depression where the land has sunk down into the area that used to be filled up by magma underground. And we know that that's just one caldera of many that we can see kind of tracking back across the West, going all the way to northeastern California, that we think are associated with the same hotspot, and then maybe the same magma source that was fueling the Columbia River basalts. And then closer to home, interestingly, we think perhaps this same mantle plume contributed to some kind of flood basalt activity a little bit south of this caldera that we can see up on the Modoc Plateau down here. So there's something that's called the Lovejoy basalts. Let me just skip forward for a minute. And the Lovejoy basalts are these basalts over here that cut across Northern California. So here's the Columbia River basalts, here's the Yellowstone hotspot, and then here's the Lovejoy basalts. And so there's some outcrops of Lovejoy basalts in Plumas County. Thompson Peak, which is in outside Susanville, so in Lassen County, I think, maybe it's in Plumas County. Anyway, it's a peak that's over a little northeast of Quincy, we think is the source that this lava erupted from on the surface. And again, it may have been tied to the same hotspot underneath the ground. But it contributed to these big basalt flows at the same time period, about 15, 16 million years ago, that spread all this dark black basaltic rock across areas that we can see in like the Chico area today, in the Oroville area today, and then all the way across the Central Valley as far away as Vacaville, which is like all the way getting into the Bay Area. So again, this isn't something that is just flowing like 5-10 miles away from a volcanic vent. These were very fluid lavas that were able to travel quite a bit of distance. And so Table Mountain, which is in Oroville today, and it's kind of famous for the pretty wildflowers that grow there in the spring. It is part of these Lovejoy basalt flows that formed at this period of time, 15, 16 million years ago. And so today it looks like this big flat top. And the way that it formed is that 16 million years ago, the landscape would have had a different shape. There would have been hills on both sides of the current day Table Mountain. And then this fluid lava would have rushed down. And then just like any other liquid, it would have found kind of the lowest point on the landscape to flow through, just like water would like flow down into a crack. Lava does the same thing. And then it would have kind of formed a smooth surface, just like water does as it fills up a container. And then eventually it would have cooled and then solidified. And then this much older rock that formed kind of the mold of the landscape around Table Mountain would have eroded away more quickly. It's made up of a different kind of material that maybe isn't as resistant to weathering or breakdown, and then it's just older rock in general. So now that rock has disappeared, and now we have Table Mountain left behind. So there's a number of these kind of plateau type features in the area around like Oroville, Paradise, and Chico, and they all would have represented the same kind of molding that would have happened in these river beds that we can't see anymore because the landscape has eroded away. So anyway, those are some local features that have been formed by these kind of flood basalt events that you've likely seen before, or maybe you'll see or notice now that you know to look for them. Okay, that's a good stopping point.